Hello, math students. Welcome to our the last melon, lesson 20 in our series on mathematics and philosophy. Last time we learned 4 valid logical forms: modus ponens, modus tollens, hypothetical syllogism, and disjunctive syllogism. We also learned 4 invalid logical forms, including affirming the consequent, denying the antecedent, hypothetical fallacy, and affirming the disjunct. Today we'll learn about the thing that Bertrand Russell is most well known for, Russell's paradox. Hey, nice Doc Martens.
By Jove, nice paradox!
No, that's not what a paradox is. Well, what is a paradox? In English class, you are normally taught something like this. A paradox is a statement that reads as being absurd or contradictory. Something's wrong with it. But upon closer examination, reveals some truth. For example, igitur qui desiderat pacem praeparat bellum. There's your Roman general. What is he saying? In order to preserve peace, we must prepare for war. Paradox, right? Trying to preserve peace, but you're going to war. Kind of funny. Here's another paradoxical statement. He that findeth his life shall lose it, and he that loseth his life for my sake shall find it. So paradoxes, they seem to be contradictory, but yet at the base of them, there's some deep fundamental truth being underscored. In logic, however, a paradox is best described as a logically self-contradictory statement, or a statement that runs contrary to one's expectations. Put another way, a paradox is a statement that, despite apparently valid reasoning from true premises, leads to a seemingly self-contradictory or a logically unacceptable conclusion. We can see mathematical or visual displays of logical paradoxes vividly in the art of M.C. Escher. Escher was a Dutch artist who lived from 1898 until 1972. He made mathematically inspired woodcuts, lithographs, and mezzotints. Here's a famous one, you've probably seen this, called Drawing Hands. Kind of a paradox, right? The beginning and the end. Where is the beginning? Where is the end? How are things generated? Self-generating. How is something possibly self-generating? Paradox, right? And here's one famous one called relativity. You can see the staircases all shift your perspective. Are they going up? Are they going down? Which way's up? Which way's down? It's all relative, I guess, right? And here's a third one that maybe you've seen before. It's called waterfall. You can see the waterfall falling here, and then the water flows this way, and it goes around the corners, back up. But is it going up? It's at the bottom, but it's at the top, but it's at the bottom. So how is that? It's kind of paradoxical waterfall. M.C. Escher. Another one, maybe you've done this in art class, or maybe you've done it in math classes. It's called a Zentangle. These are Zentangles. This is an example here, mathematical geometric pattern. The paradox of the Zentangle is that by drawing only straight lines, you derive a gently curving spiral. So for instance, you start with a triangle, and then you overlay another triangle, and overlay another triangle, and triangles go around and around, right? So it goes like this, go down here, go around, and it spins slightly, ever so slightly, and then it creates a kind of a form, which is interesting, but paradoxical. Okay, so what are some famous paradoxes anyway? Let's look at some. This is the famous paradox of Zeno, or Zeno's paradox. Zeno was a pre-Socratic philosopher from Elea, 5th century BCE. Let's watch the video.
60-second adventures in thought. Number 1. Achilles and the tortoise. How could a humble tortoise beat the legendary Greek hero Achilles in a race? The Greek philosopher Zeno liked a challenge and came up with this paradox. First, the tortoise is given a slight head start. Anyone fancying a flutter would still rush to put their money on Achilles, but Zeno pointed out that to overtake him, Achilles would first have to cover the distance to the point where the tortoise began. In that time, the tortoise would have moved, so Achilles would have to cover that distance, giving the tortoise time to amble forwards a bit more. Logically, this would carry on forever. However small the gap between them, the tortoise would still be able to move forwards while Achilles was catching up, meaning that Achilles could never overtake. Taken to an extreme, this bizarre paradox suggests that all movement is impossible. But it did lead to the realization that something finite can be divided an infinite number of times. This concept of an infinite series is used in finance to work out mortgage payments, which is why they take an infinite amount of time to pay off.
Okay, another ancient paradox is called the Cretan paradox, or sometimes it is referred to as Epimenides' paradox. Epimenides was a Cretan who made one immortal statement: all Cretans are liars. So here you have a Cretan saying all Cretans are liars. So if he says, I'm lying, and then the person listening says, wait, so you mean you're lying? But that would mean, do you see the problem? It's a paradoxical statement, right? How can you say you're lying when you're all liars? If that's a truth, how can you tell a truth if you're always a liar? See, it makes your head explode. Here's a modern version of the liar's paradox from Star Trek.
The explosive.
Very well, Captain.
Explosive!
Don't panic. We'll make children first.
Spock. Isn't that too much for our purposes?
I believe that is the correct amount, Captain. Mr. Mudd, are you ready?
Aye, aye.
Careful, I would not want you to drop it. Easy.
Detonator.
Fuse. Primer. Mashing.
There is no explosive.
No? Observe. Are you all right?
But there was no explosion.
I lied.
What? You lied. Everything Harry tells you is a lie. Remember that. Everything Harry tells you is a lie.
Now listen to this carefully, Norman. I am lying.
You say you are lying, but if everything you say is a lie, then you are telling the truth. But you cannot tell the truth because everything you say is a lie. But you lie, you tell the truth, but you cannot, for you lie. Illogical. Illogical. Please explain. You are human. Only humans can explain their behavior. Please explain.
I am not programmed to respond in that area.
Okay, so that's the liar's paradox, or the Cretan paradox. You can see how the authors of Star Trek, Gene Roddenberry, and they thought that humans were better than machines because, by golly, we're not purely logical machines. We're not purely logical beings, you know. We run by other sets of principles, and we're deeper, more rich beings than that. You can decide for yourself, I guess, about that dramatic display. The next paradox I'd like to discuss with you is Russell's paradox. This is the notation for Russell's paradox here. We can explain it. Any group of things can be called a set. Russell calls R the set of all sets that are not members of themselves. If the set R is not a member of itself, then its definition dictates that it must contain itself. But if set R does contain itself, then it contradicts its own definition as the set of all sets that are not members of themselves. See? So there's an internal contradiction here that makes it a rather paradoxical problem. This contradiction is Russell's paradox. Russell's paradox is sometimes also called the barber's paradox. Let's have a look. This is the barber's paradox. Imagine a town with a strict law on shaving. By it, every adult male is required to shave daily, but it's not obligatory to shave yourself. For those who don't want to, there is a barber. In fact, the law decrees those who don't shave themselves are shaved by the barber. Those who don't shave themselves are shaved by the barber. It sounds innocuous. However, if taken literally, it leads straight to paradox. For you see, the question arises, who will shave the barber? He obviously cannot choose to shave himself, for being the barber, it would mean that he is shaved by the man who shaves only those who don't shave themselves. Being the barber, it would mean that he is shaved by the man who shaves only those who don't shave themselves. But he can't go to the barber, for again, that will mean he'll shave himself, which the barber isn't for. So, we remember from our studies how Bertrand Russell was a logical positivist. He thought all knowledge could be reducible to logic. Russell threw out any claims to knowing that didn't seem perfectly logical or reducible to reason.
That's highly irrational, my good boy.
He wouldn't have liked Pythagoras or Plato because they drew upon ways of knowing that transcended or went beyond the strictly logical.
Idealistic nonsense, old boy.
He likewise would not have accepted Descartes' proof for the existence of God, nor would he have appreciated the visionary roots of Descartes' mathematical discoveries.
Old boy, God is simply not a probable hypothesis.
Logical paradoxes were interesting to Russell. However, sometimes paradoxes unleash scenarios that seem pretty fantastic and that reintroduce wondrous possibilities that are not strictly logical.
Preposterous!
Take, for instance, the grandfather paradox.
As far as we know, time only moves in one direction, forward. But if you could loop back to visit the universe at an earlier point in time, a famous paradox arises. What if you killed your grandfather when he was a child? Then your father or mother wouldn't have been born, so you wouldn't have been born, so you wouldn't have been able to go back in time to kill your grandfather in the first place. Paradox. The simplest resolution to the grandfather paradox is that when you go back in time, you're actually not going back into your own history, but to a copy, and everything you do there influences the new alternate future of that universe, not your own past. But that's boring because it just avoids the paradox. If what you do when you go back in time actually influences your own past, and the effects of your time travel do loop back to the present, future, past, no problem. Let's just follow the paradoxical timeline through beyond its paradoxical conclusion. You go back in time, kill your grandfather, thus you aren't born, so you can't go back in time, thus your grandfather isn't killed, thus you are born, so you go back in time and kill your grandfather, and so on. I'm showing this as a looping linear series of events, but really it's two entangled histories happening in parallel. Is that even possible? Well, I don't know about the time travel part, but subatomic particles regularly do multiple different things in parallel. It's called quantum superposition and is responsible for the weirdness of the double slit experiment, many properties of atoms and molecules, fusion in the sun's core, and so on. So if the universe were to exist in a superposition of two states, your grandfather's alive and your grandfather is dead, then the natural result is a superposition of two states. You're born and able to go back in time to kill your grandfather, and you're not born. And the natural result of these is a superposition of two states. Your grandfather is dead, and your grandfather is alive. And so, at least from a logical perspective, this looping timeline is entirely consistent and there's no paradox. And a similar paradox-free solution can be obtained by viewing the problem as a steady-state solution to a Markov chain, but I won't go into that here. Now, of course, nothing about these solutions to the grandfather paradox suggests that closed time loops are actually possible. In fact, some of the implications this kind of time loop have in the study of complexity theory seem to suggest that time loops, and thus time travel into the past, must be impossible. But the main point is sometimes we think a situation creates a paradox when it doesn't, and really the only paradox is how our thinking can be twisted enough to dream up time-traveling murderous grandsons, but not twisted enough to think about twisting time.
All right. Did that make your brain hurt? Today's philosophic experiment, students. Investigate some other paradoxes. Write about them in your journal or demonstrate them to the class. Question 2. So do you think there is any knowledge that defies logic or that transcends logic? Explain why or why not. And question 3. Now that we have completed our series on 2 ancient and 2 modern philosophers in math, think for a bit about whether you prefer ancient or modern thinkers. Tell why. Alternatively, decide which of the 4 philosophers we studied you like the best. Tell why. Okay, folks, I hope you enjoyed this series. I hope you have an excellent year in math, you learn lots, and you stay healthy. And strive after wisdom. Pursue wisdom, okay? Every day, make it a habit. It's a way of life. Try your best with it. Every day, see if you can cultivate it in your heart. Cultivate love in your heart. Take your love upwards. Take your love up towards the beautiful, the good, the true, and And this is how you will practice philosophy in whatever walk of life you get into for the rest of your life. And you make the world a better place by loving wisdom. Thank you. See you next time.
I reached the